Hi everyone, we're Group28 and our presentation is about commitment schemes in cryptography, mainly focusing on bit, vector, polynomial, and functional commitment. We aim to understand these commitment schemes by close studying on their features, including security definitions, constructions, and applications. We will also present the results of our study, including comparison and open problems. Before we dive deeper into any particular scheme, we would like to present a brief introduction. As a cryptographic protocol, a commitment scheme is mainly about a sender committing to a value, and this value cannot be changed anymore. This committed value will be confidential for the receiver until the committer decided to review it. In short, it's just like putting a note in a lockbox. Here is a vivid image that presents the general idea of commitment schemes. The locked box is the commitment, which prevents the big shifts change and ensures the confidentiality of the committed value. In this case, it's the ballot with the number 5. There are two most significant properties of the commitment schemes, binding and hiding, and this can be also seen as a foundation of the security. Binding means the committed value cannot be changed or reviewed to another different value. Just like the big shift put the ballot with the number 5 inside the box, so the little shift will get the number 5 review as the only result. It is crucial as binding ensures data integrity and it prevents cheating or fraud in cryptographic protocols. Hiding means the committed value will be confidential for all the parties until the committer decided to review it. It ensures data confidentiality. Now, Ziyu will present the first commitment scheme of today, the bit commitment.
First, let's look at bit commitment, which is the committer choose a bit 0, 1, and then use several different algorithms to compute a commitment value to send to the receiver. Then we can see the process of the bit commitment. At the top, we can see the whole process of the committings. Firstly, in the committing phase, the committer chooses the value of the bits and then use some encryption algorithm to calculate the value of the commitment and sends the results to the receiver. In the revealing phase, we can see that the committer sends the original data to the receiver, which is calculates the value and compare it with the value received in the committing phase. The following is the overall calculations process using the hash functions as the encryption algorithm. Let's look at the actual applications of the bit commitment, which has blockchain, voting systems, and so on. There are many application scenarios. We consider the security of the online cautious. We have also talked about the safety of the commitment schema. We know that hiding and binding are very important, but for different situations, we will pay more attention to one. For example, in the open auctions, binding is more critical because the auctioneer needs to see the auction price. The auctioneer cannot arbitrarily change their price when they see the real-time auction price. On the other hand, in the closed auctions, hiding is more important. Second, let's look at vector commitment. Vector commitment and bit commitment are very similar. The most significant difference is that the value chosen by the committer at the beginning of the commitment of the bits into groups of bits or numbers. At the same time, we see the new additions of two phases, initialization and the verification phase. In the initialization phase, some settings and parameters will be defined publicly and the encryption method will also be defined. In the commitment phase and the revealing phase is similar to the bit commitment. The new additions is the verification phase. This phase is similar to the revealing phase but cannot be discarded because in this phase, the receiver calculates the proofs sent by the committer to verify whether the committer has not changed the initial commitment or not. As I mentioned earlier, the vector commitment is similar to the bit commitment, so the overall application scenario is similar. I choose to introduce the method with the most vector attributes, the Merkle tree. Merkle tree is the most critical method of the verification applied in blockchain transactions. In these application scenarios, we focus more on the binding aspect because once the Merkle tree is created, the root hash uniquely represents all leaf nodes in the trees. Next, Chen Hao will introduce the last two commitment schemas.
Polynomial commitment is a cytographer commitment scheme. This scheme allows an entity to commit to a polynomial without revealing it immediately, and it can reveal a chosen point at any time without disclosing any other information. A key feature of this scheme is that it can maintain a fixed overhead when opening multiple evaluations. This means the communication cost is constant. A polynomial commitment scheme usually consists of two phrases, the commit phrase and the open phrase. In the commit phrase, the details of these are on the left side. The committer selects the polynomial and creates a commitment to represent it. For the open phrase, the committer reviews specific information about the polynomial and provides proof to ensure that the information is consistent with the original commitment. The application of polynomial commitment scheme include the verifiable secret sharing, zero acknowledgement set, content extraction signature, and credential. In the application of credential, user can prove that they have valid credential without revealing the content of it. Binding prevents the user from changing their credential without being detected. Now we reach to the functional commitment part. The term functional here refers to the scheme's ability to support the verification of certain functions or properties of committed value. Like the polynomial commitment, functional commitment includes the commit and open phrase. In the commit phrase, the sender selects the value or a set of values to generate the commitment. For the open phrase, the sender reviews the result of certain function of the chosen values rather than the value themselves. In this way, the receiver can verify the result of the function without knowing the actual values. The security of functional commitment depends on two properties, hiding and bindings. This ensures that the commitment values remain secret until to the proper time, and once the value has been committed, it cannot be changed. Functional commitment can be viewed as a generalization of vector, polynomial, and many other special types of commitment scheme. Due to the generalization aspect of the functional commitment, theoretically, it can cover the functionality of the other commitment scheme.
We compared these four schemes on aspects of implementation, pros and cons, and their applications. Bit commitment is concise and easy to implement but with low functionality as it offers commitment only in bits units. It is widely used in transaction proofs and digital payment channels such as bitcoins. While vector commitment supports commitment for a set of values and allows dynamic updates, it is relatively more complex and harder to implement. It is widely used in big data verification and data sharing. Polynomial commitment is based on mathematical structures and enable commitment costs to remain constant without the impact from degrades. It is widely used in zero-knowledge proofs and computation with multi-parties. Lastly, functional commitment is the relatively most powerful one and can handle complex scenarios. It is based on sophisticated cryptographic constructions, so it is the most difficult one to implement. It is widely used in privacy-preserving computation. Now, Chen Hao and Ziyu will present about open problems.
Performance optimization is a key issue when deploying commitment scheme. The computation efficiency and the communication overhead directly affect the system availability and user experience. Therefore, the research needs to continuously explore the new technique to improve the performance of commitment scheme. Also, there is usually a trade-off between the security and the efficiency when designing the commitment programs. For example, increasing the security of a commitment may increase the computational and the communication overhead.
Another point in the open problem is that we need to focus on new attacks such as new attack models, set channels attacks, and quantum computing. For example, in quantum computing, quantum computers have the potential to break the many existing cryptographic schemas, including commitment schemas. Quantum computers are able to solve in the polynomial time certain problems that the conventional computer takes the exponential time to solve, which may threaten the security of the commitment schemas. So the research needs to continuously investigate the new cryptographic technique and the defense strategies to cope with the possible attacks.
Our future work plan has three main aspects. We will search and document more information on application of each scheme and its related open problems. We will also review the existing works and ensure correctness. We will keep focusing on the previous two open problems and researching and document our findings and ideas. Thank you for watching our presentation, and we wish you a good day.